Good morning, 8th graders. This is just a reminder to complete your weather log if you have not yet for today, and then we will get going into energy transfer. So we have talked about energy transfer broadly ever since we talked about structures of the earth. When we were talking structures of the earth, we talked about our mantle and how there are these very specific energy currents that are moving through our mantle, allowing for our lithosphere to kind of like move on top of. Well, that is essentially energy transfer. Okay, so we will talk about more specifically the three different types of energy transfer throughout this lecture. So we are still working with Middle School Earth Science Standard 2-6, which states basically that you will be able to develop and use a model to describe the unequal heating and rotation of the Earth causing patterns of atmospheric and oceanic circulation that determines regional climate. Basically, by the end of this, you should be able to define and identify the different types of energy transfer. Remember, there's 3 of them, as well as identify the concern of the greenhouse effect due to energy transfer. So make sure you have these notes in front of you and let's get going. So solar radiation, when we talk about solar radiation, we are talking about the electromagnetic energy that is emitted from the sun. So the sun, which is way out there. And we have to understand that the earth, like 99% of the radiant energy from the sun is coming toward the earth. Now, we see this solar radiation in a spectrum worth of energy, ranging from ultraviolet radiation to infrared radiation to visible light. So actually being able to see what is on your screen right now is thanks to solar radiation. So we have to kind of put the idea that solar radiation is 100% negative because it is not. So the sun's energy on the electromagnetic scale or spectrum can come in many different ways. The 3 that we're going to focus in on though for this includes the visible light scale, the ultraviolet light, and the infrared light. So visible light is what you can see. It's the colors, the shadows, things, the reason why like the plants behind me are green and the wall is gray and that you might be wearing a red shirt and things like that. That is all based off of the visible light spectrum, which is a super duper small portion of the electromagnetic spectrum in its totality. We have then ultraviolet rays, which are very short wavelengths, but they have a high impact of energy. Such a high impact of energy that this is what like can destroy chemical bonds within our DNA. We talked in the last lesson about how ultraviolet light is being absorbed by the ozone because if it came in contact with our skin cells, we would essentially kill off those cells, causing like sunburns, or even worse, they start to multiply and mutate in a way that can cause things like melanoma and other sorts of cancers. So that is ultraviolet light. Ultraviolet light, when we're talking about it, we tend to think more along that like purpley blue sort of spectrum because it's much closer to the purpley blue side of our visible light spectrum. Infrared, like it says, we think more red. These are longer wavelengths. They come to us typically in the form of heat or thermal energy. So typically when we talk about like night vision goggles and things like that, or infrared goggles, it's because we're trying to pick up heat signatures because they're very long waves versus the very short waves that happen with ultraviolet. Now, yes, as you can see, there's so many other things. Gamma rays are real. Okay. X-rays, obviously, you get them done probably once a year when you get your teeth cleaned. Things like that. All the way to radar, FM radio, TV waves, short waves, and AM radio waves. Okay. So those are just kind of like what's going on. But the ones that we're going to focus on, because these are what we are more so seeing as far as from our sun, ultraviolet, visible, and infrared. Okay. That's it for whole group notes. If you have any questions, please feel free to ask your teachers. And if you're sticking around for the rest of lecture, awesome. Let's keep moving. So once the radiation leaves the sun and comes in contact with Earth's atmosphere, only certain percentages of it actually make it to us. So 50% of all of the radiation the sun is emitting that actually makes it to us, 50% of it is being absorbed by our surface. Okay, that's why when you step outside on bright sunny days like this, especially in the summer, the black sort of tarred roads are going to feel much, much warmer than the lighter colored driveways, things like that, because it is being absorbed. 25% of whatever radiation makes it to us from the sun gets reflected back thanks to the clouds in our sky. Granted, I'm looking outside right now, not a lot of clouds, but thanks to clouds and other particles just within our atmosphere that just are there. So it gets reflected back. 20% of all of the radiation that makes it to us from the sun is absorbed by those particles within our atmosphere. So 25 get flung right back out into like space. But 20% gets absorbed, and that's why our atmosphere tends to warm up. This would also be things like in the ozone layer and all that. And then finally, we have 5% of all of that radiation that has made it to us from the sun that's getting reflected back thanks to our light colored surfaces and water. Okay, so not everything gets absorbed. A good portion of it gets flung right back. So we're looking at about 30% gets reflected right back out into space versus we are taking in 70% either within our actual surface or our atmosphere. Here's just another way to kind of break it down. So I'm like looking at my second screen. So if we look at our solar radiation as 100%, okay, 25% of it makes it to the clouds but goes right back out, okay? 20% of it makes it to our clouds and our atmosphere and get absorbed, so it hangs out here. Okay, 5% makes it to the surface or to the land and water and then gets reflected back. And then 50% overall makes it to the earth and stays. So there's that just kind of broken down into a picture tutorial. Now, once it gets to the earth or within our atmosphere and isn't being reflected, energy then gets transferred, and it gets transferred in one of three ways: either conduction, convection, or radiation. We've talked about convection before. This is what's happening within our mantle. So it is the heating and cooling of liquid or any sort of liquid material, and it gets pushed around that way. Well, we're going to also talk about conduction, which is the physical touch of it, and radiation, which is what you feel coming off of it. So, how does this happen in our atmosphere? Well, let's talk radiation. Let's just start there. Okay, so radiation, this is the sun emitting the solar radiation out away from its core. The radiation then comes into contact with our atmosphere and starts to heat up our atmosphere. If you think about cold winter evenings, if you have a fireplace, gas or electric or whatever, okay, this is what happens. You're not physically touching the heat from the fire, but that fire is starting to come in contact with the atmosphere or the air around it, heating up the air. Okay, that is what's happening. It's heating up the particles in the air, which eventually you have your fireplace on for an hour, your whole living room probably feels warm. Okay, that is radiation. Convection. This should be the easiest out of all of them. Okay, convection, this is where radiation heats up the particles in the atmosphere. Okay, so we're with the radiation, but then the warmer particles move toward the higher altitude because we already know that heat rises and cold sinks. So as the atmosphere starts to like heat up closer to the surface, starts to heat up and go up. Well, as we learned in the last video, that as you increase in altitude in our troposphere, you decrease in temperature. So these warm particles go up towards the colder top end of our troposphere, start to cool down and sink. And then we just keep that rotation. Okay, so that is how our air is circulating within our atmosphere. We have to have the radiation that heats up the actual like atmosphere, and then it goes into that convection or that circulating. Conduction. This is really only happening within our troposphere, or let's just talk about it within our troposphere. Okay, remember the troposphere is where we live. So air is making contact. So as it increases in our altitude, it cools down, but as it comes back down, it starts to heat back up. That air comes in contact with the surface, or it comes in contact with us here on the Earth, either during the cooling or the warming process of the particles. So it might be coming down and hitting us kind of cool. So if you think of anything during the winter, we get that cooler air that kind of comes down toward us, versus in the summer, we get that warmer air coming up from the equator. Okay, so that, but it's the actual air making contact with us. Okay, so radiation is just that like heat. So if you go and you like put your hand in front of a fire, okay, it's that feeling of the heat. The convection is the movement of the heat or cooling, and then conduction is that atmosphere coming in contact with our skin. Okay, any questions on that? Ask your teacher. Hopefully I explained it well enough. So this brings on a balance, okay? Because we know that we're getting the solar radiation from the sun, but we also know that we have some heat within our Earth's core that is being emitted out. So the amount of solar radiation from the sun needs to be equal to the amount of radiation leaving Earth's surface, okay? If we don't have that equal, like hot and cold, something coming in, something going out, we get a surplus. Okay, either A, it's way too cold, and this is where we bring on ice ages, or B, it's way too hot, bringing on the greenhouse effect. So, gases in our atmosphere start to act similar to glass. Okay, and think of glass in a greenhouse. We have greenhouses, especially in this area, because we cannot grow plants or vegetation all year round, not out in the dirt, because we now, right now, don't have snow, but we could in the next like 24 hours. Who knows? Okay, so we have greenhouses to warm up specific areas so that we can have vegetation grow. So radiation that's coming in from the sun, because we can't stop that, also needs to try to leave, but sometimes it gets blocked by our gases that are creating this like glass dome, causing that extra thermal radiation to stay near the surface. Greenhouse gases can lead to an increase in thermal energy in our atmosphere, creating just too much heat. And that's where we start to see things like global warming, where you have longer, hotter months than you do the colder months. Things like that. Carbon dioxide is a greenhouse gas. Methane is a greenhouse gas. Even water vapor can start to turn into a greenhouse gas, where it just traps that heat closer to the surface. This is why we need the balance of equal and unequal heating to allow for all of this to stay like livable for multicellular life. So the greenhouse effect is essentially like putting a glass dome around the Earth and keeping everything in when we need that 70% in but 30% out sort of a process, because that's not happening everywhere, but most places. It balances itself out in the long run. I'm not a climatologist. So that's kind of what's going on with our energy transfer and how it is positively affecting and can also negatively affect our Earth. If you have any questions, because that's it for energy transfer at this point in time, we're going to start putting energy transfer and atmosphere together in the next set of notes. So, any questions, ask your teachers. If not, hopefully we're good. There should be a check-in after this. And yeah, if you need me, just let me know. Thank you, 8th graders.